All right, so we'll be going through this tutorial sheet. Not literature, it's an assignment, so it caters both open learning and distance students. Okay, so we'll be able to talk about one or two things inside there. Okay, so that is as we have now CH110 and CH120 for distance students. Even in SCOV resources, you can share this to your friends. So it was supposed to be submitted on 20th of November. All right, so let us see. So the content is this: hydrogen bonds, describe the metal structure, gas equations, effusions, stuff like that. We'll be able to crack all these stuff. All right. So without wasting our time, we can now start. All right. So the first question that we have is distinguish between all right, and intramolecular forces of attraction using water molecules as an example. All right. So when you talk about inter and intra has to talk about inside something, then inter has to talk about outside something, the way it is connected bumper to bumper. All right. So what we need to know is that all right, let me start with this one. Intramolecular forces, all right, these are forces with molecules, all right, within molecules to say, okay, so they are forces within a molecule, e.g. in water molecule, all right, in water molecule, all right, the H, because H is bonded like that, all right, so the bond between O and H, this bond here, it's what we call inside of the molecule. You get me? So that is the intramolecular force. Okay. Intra has to talk about inside. I said intramolecular, these are just forces within a molecule, e.g. in water. We have given an example, and the best example we can also again outline is OH and water, or in water molecule, in one more water molecule. All right. In this one water molecule, we can have these intramolecular forces. Then, when I talk about intermolecular forces, these are forces between molecules, e.g., hydrogen bonds forms between different water molecules. So, for example, I want to connect a lot of water molecules. What I'm going to say is, in different water molecules, let's say we have H2 plus again H2, all right? So they will be bonded like hydrogen, all right? Or two like that, all right? Again, hydrogen, all right? Again, another hydrogen of another water molecule, right? So this bond between hydrogens in water molecules is what you call intermolecular forces, all right? It's between different two water molecules. So that's what we mean when we say intra. So in summary, I'm saying intra, all right? Intramolecular forces, these are forces within the molecules, e.g. I've given an example here. Then intermolecular forces, these are forces um between different molecules. I can say like that. Okay, there's no harm. So you can say intermolecular forces, which are intermolecular forces, are forces between molecules. All right. So that makes it clear, hope. So we go to question B. Describe the following types of all right, molecular forces, giving a suitable example. Okay. So when you say hydrogen bonds, all right, what are these hydrogen bonds? These are just strong, okay, intermolecular forces formed when hydrogen is bonded to or to just an electronegative atoms such as, okay, neon, oxygen, not neon, nitrogen, fluorine, okay. So hydrogen bonds are bonds, they are all right, molecular forces when hydrogen is bonded to the electronegativity element or atom such as nitrogen, hydrogen, fluorine, chlorine, stuff like that. Those elements with the high electronegativity. Yes, something has entered my eyes. Ah, okay, that is it. So I said these are just strong. They are strong, by the way, for hydrogen because of these electronegativity. More electron. It's not easy to remove the bond between hydrogen and fluorine. Why? Because this guy is more electronegativity, and it will try by all means to pull the electrons shared. So that means this is the type of bonds or intermolecular force. Um, this is the type of intermolecular force that is strong, that involve more electronegative elements such as fluorine, chlorine, stuff like that. Okay, so these are the hydrogen bonds that we know. They are one of the strong bonds that we have. Then we have random forces. So random same as dispersion forces. All right. So it's also called dispersion. So when you hear the word dispersion, just know that they are talking about London. They are London like that. Okay, or London. Okay. So London forces. These are forces caused by temporary dipole, right? Due to movement of electron. So suppose I have the force, okay? The force that will be, let's say, carbon and hydrogen there, all right? So as a result of we are demarcating this, okay, the dipole, because this is more electronegative and this is what? Less electron. So this will be more, or this is more electronegative, this is it, less the. So the dipole, the charge, the change in charges is what we call dipole, right? So I'm saying these London forces, they are forces or dispersion forces caused by temporary dipole. Okay, so the dipole temporary that are formed, like I demonstrated a plus there and a negative. When we demarcate this bond, we have a positive there, then a negative from hydrogen. So this force is the one actually causing this. Okay, we call it random. They break randomly unknowingly, so that's what we call random. So I repeat again: random forces or dispersion forces, these are forces caused by temporary dipole due to the movement of these electrons between the bonds. For example, iodine 2 there. Okay, I can separate this iodine molecule. I can separate like that. All right, so like that. Once I separate these, then that means we have random forces. All right, so these are forces caused by temporary dipole due to the movement of electrons. Okay, so electrons, once they move, they go, let's say, to this side, and this will be charged negative, then this will be charged positive. All right, so we call it inductive effect, where the other one is charged negative, the other one positive. They can't get equal, they have to share different like that. So this is what we causes that. It's called random or dispersion force. Then we have what we call dipole forces. What are these dipole forces? So when we talk about dipole forces, all right, these are forces caused by due to the attraction between permanent dipoles, all right, in a polar molecules, such as, when I say polar, non-polar, something which is non-polar is of the same, right? This. But when I say non-polar is something, let's say hydrogen, chlorine, all right? So I'm saying dipole molecule, forces, these are forces caused due to attraction between permanent dipole in polar molecules. This molecule is polar because of different electronegativity, all right? So these ones, they actually attract dipole. They are the result of attraction between these two different polar molecules. Then random, they are the result of what? Temporary, all right? So this is permanent, all right, dipole. Then this one is temporary dipole, just temporary. Then this one, just know that this one is temporary. This one, this one is temporary. This one is what? Permanent. I'll repeat. Dipole forces. These are forces caused due to attraction between permanent dipoles in polar molecules like hydrochloric acid, like that. These are permanent polar molecules. Then we have random. I gave an example of hydrogen plus carbon like that. So these are forces caused by temporary dipole due to the movement of electrons. So once we leave that, that will be negative, then that will be what? Positive there once electrons is shared. So they can only bond with the different charges like that. So that is what I mean when say random forces. They are random and break this and remain with this dipole moment. Hope you have taken note of where I said the definition. Now repeat the definition. Random forces, these are forces caused by temporary dipole due to the movement electrons or withdrawing, e.g. between, all right, e.g. between iodine, all right. I can put iodine there, iodine molecules. Jared, bro. Okay, so that is it about random forces. I said these random forces, I said these are forces caused by temporary dipole due to the what? The movement of electrons. All right. And for hydrogen bonds, I said these are strong intermolecular forces. These are strong intermolecular forces caused by when hydrogen is bonded to more electronegativity elements such as fluorine, stuff like that. Okay. So there are elements that forms hydrogen bonds when hydrogen is bonded to what? To more electronegativity element. So that is it. Then for random forces, I said these are weak forces caused by what? Temporary what? Dipole. I mean dipole due to the movement of what? Withdrawing electrons or due to the movement of electrons. E.g. this and this will remain with the negative and the positive there. So these are what we call random. They are not strong, they are weak. These ones, they are very permanent. The dipole forces, they are caused due to the attraction between permanent dipoles like hydrochloric acid, and these are permanent dipoles that we ever experience. In polar molecules, different charges. This is negative, this will be positive charged. So those are all dipole moments. Then to discuss the difference between ionic bonds and covalent bonds in terms of electron movement and electronegativity differences. Okay. Uh, why? Why so? Okay. I think there's something causing this. Let me just change. Okay. So you master. Random forces, they are weak. Okay. Dipole, they are just caused by attraction between permanent dipoles. All right. So then now we are to discuss the difference. So we are discussing the difference between, okay, the difference between ionic bonding and covalent bonding in terms of electron movement and electron difference, electronegativity difference. All right. So we need to talk about that. So first of all, ionic bonds involve, in terms of electron movement, ionic bonds, all right, here, all right, ionic. So this involve transfer of electrons, all right, while um while all right, the while I'll be putting for covalent. So while covalent you involve sharing of electrons. All right, so let this one be dash, then covalent be what? A star, like that. Okay, so that is in terms of electron movement. This one, the electrons are shared. This one, electrons are transferred. Okay, then the other thing that we need to talk about is that ionic compounds or ionic bonds form with large electronegativity. Okay, so the electronegativity should be at least more than 1.7 for ionic. Then that is electronegativity. Okay, then for covalent, it should be less than this 1.7. Okay, that is for covalent bond. So this is in terms of electronegativity, in terms of electron movement. So that's how we should differentiate the two. So electron movement, this one involve transfer, this one involve sharing. Then in terms of electronegativity, this is for ionic is what? great or equal to 1.7. This is what? Less or just less 1.7. Okay. Then the other question we have is to list the two properties of ionic compound and two properties of covalent compounds. So when you talk about ionic compounds, these ionic compounds, they have high boiling point and melting, all right? And melting point. Then they also conduct, these are the ionic I'm talking about. Now they have high, all right, boiling and melting point, also conduct electrons, I mean electricity in molten state. Conduct, e.g. sodium chloride, you put salt in water, you'll be able to conduct electricity. So conduct electricity in molten, okay, when you dip them in water, like what I mean salt, okay, that's molten state. So that is it, all right. Then when you talk about now covalent compounds, what are the characteristics or properties? Covalent compounds, they have low boiling point. Okay, so we are talking about covalents now, low boiling and melting points. Okay, so again, the other thing that we say, they do not conduct electricity, do not conduct electricity. Okay, so that is it about the properties of ionic compounds and the covalent compound. So the other question now that we need to attempt is answer the following questions based in metallic bonding. Describe the structure of a metal. So metals are bonded like this. Let's say there are two electrons there. All right. Okay. So again, let's say they are bonded like that. Right. Let's say for copper, it will be bonded like this. Okay. So they are free electrons. They are what we call free electrons. All right. So these are delocalized electrons. They can move from one place to another, all right, within the metal lattice. So this metal lattice, what happens that if you are to put, let's say, a charge here, the electrons that was there, it will charge this, and if finally you'll be able to hear the electricity here being, you can electrocute it. Why? Because the electrons are delocalized inside. So it's about the sea of delocalized electrons that will be able actually to transfer heat and what? Electricity. So electricity is charged to these electrons, which is there. This electron is mobile within the lattice structure. It will contact this and this within milliseconds, and you'll be able to feel the electricity, or just the heat will also be moving slowly until you feel it. That's the reason you'll be able to feel the pot that it's hot. Why? It's because of these delocalized electrons that are actually mobile, like within the structure, making a sea of electrons where the concentration matters. So that is it about this. So, metallic bonding. Okay. So the metallic bonding that I'm talking about is that metal one, they consist positive charges. So these are the points you need. So you say it consists of positive ions, like I said, positive ions. You can put 3 ions, 3 plus. These are the points that I'm just give you for this to describe the structure. Okay. The other thing that we need to say is that um, these electrons are the one actually involved in charge of transferring heat and electricity. So we are done. So explain how this structure account for the metal ability to conduct it. They are what you call um, and they are able to conduct electricity. Why? Because of electrons that move freely within the structure. So I've explained this. So it's because of electrons that are free, delocalized electrons that are free in the structure to transfer electricity within the structure. Let's say within the metal or the N copper wire. Okay. So discuss how alloying. Alloying is about we combine, let's say, brass plus copper to make, let's say, bronze. All right, I'm just giving an example. We make more strong metals using what? Two metals that are strong. Again, we combine them to make more strongly. That's what we mean alloy. Alloying is actually the process of combining two or more metals to make more harder metals. All right. So that is it when you say alloying. Alloying. All right. So now they say describe how alloying affects the physical properties of a metal. Suppose a metal had so it will actually distort the lattice structure, the arrangement, because these two metals has to bond. Okay, so so it increase the entropy. Entropy is about disorder of particles or arrangement. So one increase the I can say increase entropy. All right. The other thing that I'll talk about is that um it will also increase the strength because it will be more hard. Okay. Then the other thing that it will reduce also the effect, it will reduce the malleability of a metal. Reduce, when we know what it means to malleability, like the way to be giving that sound. Okay, so even the way the structure, you can change it into different structure, it will reduce. Okay, because the metal will increase. Okay, so that is it. There are a lot. Okay, you can talk of general stuff that you think when you combine two metals, the boiling point also changes. Okay, okay, so it brings about variability or variation in boiling points. So those are the things. So that is it about these alloying. Alloying will actually affect your metal because you want to make more strong, and you are also affecting others in one way you can't realize. Okay. So the other things that we need to talk about is um we need to talk about ideal gases. So the question that we have is, all right, ideal gases are theoretical gases that perfect follow the assumption of kinetic molecular molecules. I've been talking about kinetic molecular theories. What are these? There are four kinetic molecular assumptions that will enable a gas to obey a gas equation or ideal gas equation, which I've been preaching each and every day. So the ideal gas equation is given as PV is equals to nRT. All right. So what matters is that all the gases that will be obeying this ideal gas are actually, they follow what we call kinetic molecular theory of gases. There are four assumptions. One of the assumptions are, all right, why can I even light them? So one of the assumptions is that, I don't know if I can be lighting here. Okay, the first assumption is that gas particles move randomly. We know this. Gas particles move randomly. Okay. Okay, that's one assumption. Then the second assumption is volume of these particles, these gases, let's say they are in a vessels like that, we neglect the volume because if we just measure the volume of the vessel, not the volume of themselves. All right. So that's one assumption, because the volume that we put is of the vessels, not of the particles. That will actually be solved in Van Dyke's equation, where we'll change the volume and the pressure itself. Okay. Then gas particles move randomly. That's one point I remember. I remember saying this. Then we have again another point that I can give it to say volume is neglected. Okay. So volume of particles, volume of gases, all right, or particles is negligible. Okay, you don't have to consider the volume. All right. Then number third point, I was saying between these molecules that will be found, because there must be no attraction. If there is attraction between them, there is a force which causes attraction, then this point will be not valid, because we said they move randomly without any force. So no force of attraction. So there's no force of attraction between these particles. Okay. Then the fourth one is collision is elastic, all right, meaning kinetic theory is conserved. For example, if we collide this one with this one, okay, once they collide, they need to move independent, not sticking together. No, remember all the points that we have been saying. There's no force causing them to attract. So even their movement is purely elastic, not inelastic, but elastic. Okay, collisions are perfect inelastic. So collisions, their collision with the walls and the other particles, they are elastic, meaning they move again, they maintain the kinetic energy within them that carries them. Because if something is elastic, it means it actually collide, let's say like that, a ball and also another ball. They'll move different balls in different directions. But if it is inelastic, it means they will stick together, and that means there's a force which has caused them to stick together. So we don't want that in our study. So these are the four assumptions that we have been talking about. So the other question is, state we have gotten this. Explain why real gases deviate from ideal gas, okay, at low temperature. So we have talking about low temperature and the high pressure. Okay, so yes, these are challenges that we face under these real gases. Okay, so these real gases, okay, what we need to know is that yes, there is an effect under low temperature and also under high pressure. Why? How does that happen? We need to know that real gases, they will deviate because at low temperature attraction becomes so important to us that we should study. Why? Low temperature will cause, suppose 0 degrees, these particles, they will stick together. So what I'm trying to say is, the question is, say, explain why gases deviate from ideal gas behavior at a low temperature and also at high temperature. So I'm explaining at low temperature. At low temperature actually, it's giving us the significant actual unawareness or matter. So it actually gives us to say, at low temperature, attraction, it will become so important or so vital, so significant, all right, because the particles can actually, for example, at 0 degree or negative 30 degrees, okay, particles will stick together, you see. So ideal gases deviate from ideal gas, so they will deviate from there. Okay, so they will no longer be ideal gas because the assumption of ideal gases are these. And if we have low temperature, it means the gases will deviate from this concept, from these assumptions. Then at high temperature, okay, at high temperature, particle volume also matters. Why? High pressure, I mean, at high pressure, if we have high pressure, then we actually increase pressure. Then the volume also what is considered, because as in as much as we compress these two, okay, the volume of them also will become significant. Remember, we said in the volume is negligible, but at low pressure, in that we are reducing the vessels now where they are placed in, but the volume also will matter, because there will be a point whereby there are a lot of particles and we can't compress them anymore. So the volume of particles matters in that as well. You've seen. So those are the two reasons to explain why new gases deviate from this behavior that we actually talked about. One, I said new gases will deviate because at low temperature attractions become significant. All right, I explained this. Then, and also at low temperature, I mean at high temperature, all right, at high temperature particles volume matters. Why? Because they will be actually limiting the compressing extent. All right. So that is it. So the other question that we have is to derive the ideal gas laws from three individual laws: Boyle's law, Charles' law, Avogadro's law. Okay, that is true. This is where we actually get these ideal gas equations from these three laws. Okay. So the first thing that we need to understand is, okay, the first thing that we need to understand is we need to know that, okay, Charles' law, all right, Charles' law, first let me start with Boyle's law. Boyle's law is saying volume will be inversely proportional to what? To pressure. Then Charles' law says that volume will be equal to what? Temperature. Remember, there is always, whenever each variation is done or in each relationship is actually, um, okay, let me just lab this. Hope I'm not fast. So this volume under Boyle's law, it's saying there's a constant there, all right? Then over the pressure, it's inversely proportional to its pressure at constant temperature, all right? Then for Charles now, this is Charles, all right? Charles' law says that volume is actually direct proportion to its temperature, all right? So this means there's a K and also the temperature duration. Then for Avogadro's, he's saying number of moles, equal volume containing equal number of moles. So there's also a K and also number of moles there. So remember, the thing is about volume. So let's see how this volume actually affect one way or the other. So the volume under boys gives what? Over pressure. The volume under, there's always a K, by the way. The volume under Charles is giving direct to what? To temperature. The volume under Avogadro's is giving direct to the number of moles. All right. So this means that V is equals to K, or let me say R T K, all right, over P. So this means that this will be P, Vp is equals to N. R will be our gas constant, which is R, which will be having 0. All right, 0.8, all right, 0.2, like that. Okay, or sometimes it is 8.314 joules per mole Kelvin. Even here there's 80 moles Kelvin, just like this. So this is in short the R constant. Don't mind about that, but I'm just saying it to say R is what? K. All right. So that's the gas constant you have been using. You know the gas constant. So this means that we have R there, then T. So finally, this is the equation that we need to have. Vp, all right, is equals to nRT. So hence the ideal gas equation, all right, or gas law. This is the one you have derived from these two guys. Okay, define the term effusion. Want to define the term effusion, all right? So we are defining the term effusion, and we will explain why helium effuse faster. Effuse is about like uh diffusing into something faster, all right? So that is effusion. So if I'm to define effusion will be the movement of gas through a tin hole under a pressure, under the influence of pressure, all right? So let's say a tire is there, then there's a nail. The slow puncture that we experience, the air that is coming, that is effusion. As a result of pressure inside, then this thing is being given out. So if you have main gases, the one which is less in molar mass will be effusing faster at that hole. All right, at that hole. So that is the effusion in simple terms. You need to picture the scenario. So what I'm trying to say is the fusion is the movement of gas through a tin wall, all right, under the force of pressure. Then that is it, we have defined the fusion. Then explain why helium fuse faster than carbon. Okay, helium is having, should be, let me say, 4 molar mass, then meaning that is smaller than carbon, which is what should be 12, like that. Okay, so this means that helium will fuse fast. Why? Because it has a low molar mass. This one, then carbon. It's more like this carbon is big, this one is smaller. That is it. You can compare it like that. So that's the reason you need to give there. Very simple, right? So hope I've made myself clear. Master the way we have come up with the relationship are these for the 3 gases that we have been talking about. So you can even Charles Boyce says that at constant temperature, the volume of a fixed mass is inversely proportional to its pressure. That is for Boyce. Then for Charles' law, it says the volume at constant pressure is directly proportional to what? To temperature. Then the volume at equal volumes contain equal number of what? Moles. That is Avogadro. So that's how you actually predict. Define or state the 3 laws. Okay. So that is it. Let's go, guys. Let's go. We're almost there. So the other question says, all right. The other question says a sample of oxygen occupies 500, all right, kilopascals, what would be its volume if the pressure is increased to at constant temperature? So constant temperature actually talks about boils law, where volume will be equal to 1 over P at constant pressure, meaning that there is a constant there. So this constant, it will be, we multiply that, that will be Vp is constant. So Vp again can produce Vp2. So this means that the volume, the Boyle's law, it says V1, okay, P1 is equal to V2 P2. All right. So this is the relationship for Boyle's law. I've been talking about this. It's not something new. Okay. Follow our gas tutorials, lessons. So from there, then what we substitute now, volume one we have is what? 500. Okay, don't forget about, because I've seen there's a relationship of kilo. There's nothing to change there. So everything is uniform. Okay. So they will counter cancel. So I'll just write times, what is the P1? Pressure one is 1000, like that. Okay, is equals to 120 pressure one, and in pressure two, which is 125. Then we'll be finding V2. So we divide throughout by what? 125. So our V2 will be equal to, when you punch that on your calculator, it's giving me 400 centimeter cubed, like the way I found the other volume. All right. But yes, the standard units should be decimeter. But this is how we found, and we have no power to change it. So that is it. A sample of an unknown gas occupies a volume of what? That's another question. So in as much as you are reading this, you need to analyze whether it's Boyle's law, Charles law, or stuff like that. Okay. So a sample of a gas of a known gas occupies a volume of what? 15.0, or just 15 liters at a pressure of this one. Okay. Okay, at temperature of this one, calculate the molar mass of the gas, given the mass of the gas as. So this is coming from ideal gas. We could see the way ideal gases was changing. So we could have PV is equals to nRT. All right. So we're solving this. We need to know that this number of moles is gotten by, from molar mass concept, is equals to mass over molar mass, right? Then R T, right? This is, I've changed nothing there. So the question is asking me calculate the molar mass. So I'm calculating this molar mass. The mass have been given. The R we have constant. The temperature is also there. The pascals we have, but we need to take it into what? Into ATM. Okay. So this is where just we have an issue. The rest we just substitute the volume we have there, everything. So we need to change this Pascal. We need to know that 10, 13, all right, 10, 13, 25 pascals, all right, is equals to 1 ATM. All right. So this means that we have how many? Short, just divide that Pascal we have with this one, and you'll be able to have our volume. All right. Okay. So once we have that, we can punch on our calculator by saying we are looking for this one, right? So I'll say molar mass. Okay, this is M, all right, R T, okay, over this. Now divide when that goes there, so that will be PV. All right, that's how we actually work with this. So we substitute now. Okay, molar mass, the mass given is what? 3.60 times the other gas constant is 0.82, 0.0821 or 06 there, then times the temperature now is what? 298, right, over, okay, the pressure. Now I said that pressure we have there, divided by 10, 13, 25, which is that relationship we looked at those. Okay, we said 1 ATM, all right, is equals to 10, 13, 25 Pascal. The same 1 ATM is 760 toes, all right, and the same 1 ATM is 760 millimeter of mercury. Okay, just to recall those things, then use that conversion to take into. So that means that I have that pressure pascals. So I'll say 121,590. Then divide by what? By 10, 13, 25 times the volume is what? The volume is now given as 15 liters. Okay, so 15 liters. So when you start with this one, punch that. I'm punching me on my calculator. Where's my calculator? Okay. Okay, when I punch this, it's giving me the molar mass as the 4.88. So 4.88 grams per mole. All right, so that is it. That's how simple it can be if you actually convert those units. So it will come out, always molar mass is measured in grams per mole, just like each individual atom that actually the value that is given on the periodic table. So those are the molar mass we're talking about. And the mass was given there, all right? So the other question now that we have is, which is the last question, I guess. All right. Okay, there's something wrong with my PC, but I'm working on it. And I'm setting the PC to inbox me the line. Let me put my line there. So if you need more lessons, you can actually inbox. No, not this one. The WhatsApp line. Okay, 0964 122 411. Okay. So we are going to our question. Okay. The instruction was to answer all the questions. So that's how sweet it was, this tutorial sheet. It's important that you go through it. You have an ideas. That's all. It's not that hard. It's your future. So that is it. So now we are actually attempting this question to say calculate the pressure of exerted by this number of moles in nitrogen in, all right, 100 point something, like what is in short just one, right? That's just one. Okay, container at 25 degrees. So we need to change only temperature is not in its standard. So say 225 degrees plus 273.15. All right. So we add that, we're getting Kelvin. So that would be what? 298 298.15 Kelvin. So that is our temperature that we use. So using the ideal gas equation, so we know that ideal gas equation is given as, okay, PV is equals to nRT, right? So this means that pressure, right? Pressure is what? Do you have pressure there? Okay, so for this case, we don't have pressure, right? We are looking for the same pressure, calculate pressure, right? So say pressure is equals to nRT over volume, all right? It's just a matter of substituting. Number of moles is 0. All right, 0.5000. Just put everything the way it has come. No need to argue. Then times the gas constant is now 0.0821. Okay, then times the temperature is now 290 what? 298.15. All right, over. Okay, so the volume now that we have, put the way it is there. I don't want you to start again to say those zeros they are significant, but just put the way it is like that. So when you punch that on your calculator, for me it's giving me 1.23 times 10 to the power 10, to the power 6. This is the ATM. Okay, no, this is not ATM. This is, let me check. Okay, we're using ideal gas equation. So this is ATM because I would have said Pascal, but you can even say Pascal, but because of this guy is having ATM per more what? Kelvin. So the moles goes with that, and the Kelvin goes that, and the it goes like that. Okay, so that is the answer you needed. Okay, so this would have been given the same using the Van Dyke's equation, because the Van Dyke's equation is given as, but there are other spices that are lacking. Van Dyke's equation is given as P, all right, plus there was change in just pressure from ideal gas equation. P is equals to nRT, all right. There was change in pressure because particles, I explained that, I explained in the last video. So we have A and change in the moles over volume. That's how pressure changed. Then the volume part now. The volume part changed, like volume, there was also a constant number of moles, then plus constant B, then is equals to nRT. Okay, so they have calculated this pressure, but we don't have the A and the B. Those are the things we are lacking in our equation. Okay, so different gases, like calculate the gas of nitrogen, it has its own what, but you don't have those. Okay, we don't have those. So they have calculated. So you look at the table, we are not given the data for nitrogen, the value of A and B. Each element is given, all right? And if it is given, you'll be able to calculate the pressure finally. All right, so that is it. Just find a constant there and also constant there, constant there, constant there inside there, and you'll be able to find the pressure. But just know that it will give you the same 2 3 times 10 the power 6 atm. So that is it. So that's how sweet and simple this assignment was. I don't have to conclude the value of, I don't I can lie the value of B and D and C for, I mean B and A for the gas called nitrogen. All right, so that is it. So all those things, actually go through them, get a book, you watch the video as whatever I was talking, like you have to actually watch the first time, second you start writing if you want. But the best is the moment you start watching, start writing, then you revise if you want. Like we have a lot under chemistry. Just inbox the number, I've already written it there. So it's up to you. Thank you.